Okay, so hi everyone. So for this topic, I will discuss the four-bar mechanisms. So previously we've discussed um, degrees of freedom, no? But for this specific topic, we will now discuss a specific arrangement of a kinematic chain, which are four-bar linkages. So a four-bar linkage or a four-bar mechanism is basically just composed of four links, no? And all of them are lower pairs. No? So you have revolute pairs only. And why is this important? Because a lot of um, useful mechanisms are derived from the four-bar mechanism. No? So in designing of a machine, you have to consider simplicity because if it is simple, it is easier to build, it is easier to maintain, and it also has a lower cost. So let's discuss the different types of four-bar mechanisms and also um, how do we describe a four-bar mechanism? What are the parameters that are important to describe a four-bar mechanism? So the first link that we have here is the frame. So the frame here, this is the black, this line here, this horizontal line that is not moving. The second link is the driver or the crank. So it drives the motion, no? And usually the driver is also the one that can fully rotate, no? Usually. And then we have the rocker. So the rocker usually just rocks, no? It doesn't, well, most of the time it doesn't really revolve, no? Fully revolve, no? And then the last one is the coupler or the connecting rod, which is the green one. Okay? So with this in mind, we have four, we can really have a different, I mean for a single arrangement of a four-bar linkages, we can change the configuration by changing one link. No? So the frame is usually what we are changing here. So if we have our first configuration here, in the leftmost one, we can invert or we can create an inversion of this four-bar linkage by changing the link here, that is this one unit long into this 1.2 long. So as you can see, we change this, but everything is still adjacent as it is. No? So we just fix this 1.2 unit link, and we have a different, no, motion, relative motion of these links. So from the first, no, we can call this the first inversion. No? We can derive this second inversion, no, that has a different mechanism. So this one can revolve, this crank can revolve, but this one can only rock. No, we have a double rocker system for the second inversion. And then for the third inversion, you can change that again. So you can fix the 1.4 link, no, 1.4 unit link, and you can have another different arrangement. No? And then the last one, you have a double crank scheme wherein both of this rocker and crank can fully rotate. No? So if you change this fixed length into the shortest length, no, as you can see here, it can fully revolve. No? So again, no, you can create a different arrangement of a mechanism using your original mechanism, and it's called an inversion. And usually the number of inversions that you can have is actually four, no, depending on the number of links. So if you have four links, you have four inversions that you can create. So now we have the degrees of freedom, but we also have the Grashof's criterion. Now, the purpose of the Grashof's criterion is to define, or sorry, or to understand if one link can fully revolve. No? And this is especially important um, for when you will need to install an electric motor, so that you will understand which part of the revolute pair should the motor exist, no? So it can be classified into three classifications. We have the Grashof chain, we have the non-Grashof chain, and you have the transition chain. So the Grashof's criterion is similar to the degrees of freedom, but we have the we have the lengths of the links that we have to understand, or the relationship of their lengths, no? And we can define them as Grashof or non-Grashof chain. So transition chain is much more of a special type of Grashof chain. No? It is also a Grashof chain. So it is considered a Grashof chain if it is satisfied. No? This criterion is satisfied. So the only thing that you'd have to take note, no, is that this only applies for a 4-bar mechanism or a 4-bar linkage. So you have to take note also of the lengths of your 4-bar linkage. So you have to determine the minimum, the shortest length, L min, and the largest length, L max, and then the other links, which are L prime and L double prime. So that is only the thing that you have to consider. You have to find the shortest and longest, and then everything else. So if this is true, if you add the lengths of the shortest link and the largest link or the longest link, and it is still lower to the combination of the other two links, then it is considered again as a Grashof chain. So let's say you have an existing Grashof chain, then you can actually invert. No, you can create an inversion of your Grashof chain, and it will have I think three types of mechanisms. So the first type of mechanism is the crank rocker mechanism. So as we've discussed before, we have a crank, which is the red, we have the rocker as the blue, and the connecting rod as the green, and the frame as the black. So if you say crank and rocker mechanism, so one can fully revolve, a crank can fully revolve, and a rocker can only oscillate. So that's it, a crank and rocker mechanism. And the thing that you have to understand here, is that I mean, to really spot if this is a crank and rocker mechanism, you have to first verify if it is a Grashof chain. First thing, if it is a Grashof chain, you should check the shortest link only. So the shortest link should be adjacent to the frame. So in this case, you have the shortest link is L2, and the frame here is AD. So it is adjacent to the frame. So therefore, it is a crank and rocker mechanism. And this shortest link can revolve, full 360 degrees. And the other, so the other link here, CD, which is also the rocker, can only oscillate, less than 180 degrees. So we can check if this is a Grashof chain, we can check. So what is the longest and the shortest link? So the shortest link here is this L2. The longest link is 55. So you can add this 2, so you have 75. And this should be lower than the sum of the other links. So you have 40 and 45, which is 85. So if you do this, so you have 75. For the other links, you have 85. So this is less than, or the combination of the longest and the shortest link is still less than the other, or the sum of the other links. Then this is again a Grashof chain. Okay. So moving on, we have another type. If you invert, you change again the frame of your 4-bar mechanism, you can create a double rock or double rocker system or double rocker mechanism. So basically, both of them can only rock, they can only oscillate, they cannot fully revolve. So the one thing that you should consider or should take note of is that if the shortest link, we're still talking about the shortest link. If the shortest link is the coupler, then it is a double rock mechanism. Okay, assuming it is a Grashof chain. So in this case, the shortest link is 20. So therefore, we can consider this as a double rock or double rocker mechanism. So they cannot fully revolve, as you can see. They can only oscillate. This AB link and this CD link, or L2 and L4. And then the last one, we have the double crank mechanism, wherein when we say crank, it can fully revolve. So you have two cranks that can fully revolve, and as you can see now, what can you observe is that the shortest link should be the frame, right? So if the shortest link here is the frame, then it is a double crank, no? So you can fully revolve on this both links, both AB and CD links, or L2 and L4. Okay, so it's that simple, no? So now, if let's say you have a forward mechanism, it doesn't follow the criterion. So meaning the largest and the shortest links are greater than the sum of the other links, then there's still analysis to this, no? Or there's still definition. We can still identify what will happen, no? But usually the non-Grashof chain cannot fully revolve, no? Or no link there can fully revolve. They can only oscillate. That is one thing that you should understand, no? So you can still invert, no? The non-Grashof chain, and usually it will only be composed of double rocker systems, or double rocker mechanisms. So there are no other configurations other than double rocker mechanisms for non-Grashof chains. Okay, but it can oscillate more than 180 degrees, as we can see in these examples. So we have, I think, three configurations or four configurations for the inversion of a non-Grashof chain. So the first one is the inward-inward mechanism. So going back from the Grashof chain or to the Grashof chain, we always consider the shortest link, no? But for non-Grashof chain, we will now consider the longest link. So we will take note of the longest link for non-Grashof chain, wherein if the longest link here for this first example is that the frame is the longest link, then we have an inward-inward mechanism. So what do you mean by that? So for this example, the longest link is 50. And if you find, no, I think there's a computation here. So if you combine the longest and the shortest link, it will be 70. And the other links, if you sum them, so 70 is greater than 65. Therefore, it is a non-Grashof chain. So we can identify this as an inward-inward mechanism because the longest link is the frame, no? So why is it called inward-inward? So as you can see, it is inward in motion, no? So basically inward, no? Inward of their motion, no? So inward, okay? So that's it for inward-inward, no? It is that simple. So moving on to another inversion of the non-Grashof chain, we have the inward-outward mechanism. So we will take note at this point, the longest link again, which is this AB, no? So you have an adjacent longest link to the frame. So if you have a frame, if the adjacent link there, one of the adjacent link is the longest link, then it will be an inward-outward system. So let's check this, no? So as you can see, one is inward, the longest link is inward, the shortest link, no? Or the the other link na lang, no? The other rocker, which is this green, will be outward, no, of this mechanism. Okay. So moving on, we have also the last one, the outward mechanism. So if the longest link is the coupler, as you can see here, so L3 or the coupler, no, the connecting rod between the two cranks or the two rockers. It depends really if it is called a crank or a rocker, but anyways, it can be used interchangeably. So if this longest link is the coupler, then it is an outward mechanism. So as you can see here, if you try to revolve this forward mechanism, it cannot fully revolve, but it will only have an outward motion. Okay. So lastly, no, so again, we have three categories, but actually we have only two categories of the Grashof's criterion, no? Grashof and non-Grashof. So the transition chain is actually still a Grashof chain, by definition, but it is a special case of the Grashof chain, no? So it is in a transition in between the Grashof and the non-Grashof. That is why it is called the transition chain. But basically, if the criterion is equal naman, no? If this is equal, it is called a transition chain. So usually the characteristic of a transition chain is all of them will be what do you call this? All of them will be double cranks, no? So most of the time the links or the two links can fully revolve, no, within their axis, no. And another characteristic of transition chain is that there is some way a transition, no, that can happen within this mechanism wherein it could change direction, no. I will explain that later for this example, no. So the first basic mechanism is the parallelogram mechanism, wherein if you have, well, basically a parallelogram, so you have two equal sides, opposite sides, and basically if you sum these two, you will have an equal, no, in the Grashof's criterion. So these two can fully revolve, as you can see. If you can imagine, you can fully revolve link AB and CD. But what I'm trying to say here is that in some cases, it can flip, no? So if you can imagine, it can somewhat flip, no? So originally, the direction of your rotation will be counterclockwise for this case. But if you can imagine, in some cases, it can flip, no? Wherein one can revolve clockwise and one can revolve counterclockwise, no? In some way, no? So it's kind of in a transition between the Grashof and the non-Grashof, no? It can become somewhat way a rocker, no? For this example. I think the direction is far off here, no? But anyways. So another inversion of the transition chain is the deltoid or kite mechanism. So the best way to describe this is that it looks like a deltoid or a kite. So the equal links are adjacent to one another. Oh. So the shortest links are adjacent to one another, which are equal usually, no? The longest links are also equal. No? So you can rotate this freely, this AB, and then L4 can only oscillate. No? So the rhombus mechanism is when one of the adjacent links, no, or actually the shortest link, is held fixed. No, comparing this to the kite mechanism, the longest link is fixed. For rhombus mechanism, it is still a kite, no, but the shortest link is fixed. Okay, so as you can see, this AB can fully revolve, but the motion here, no, but it is not really seen here, but I think you can see the motion here. As AB rotates, no, this link AB rotates, this BC, no, actually just moves in this direction. No? Okay. So moving on from the Grashof different classification, let's now move on to the slider and crank mechanism. Uh, so usually in four-bar linkages, we just have this rotation, motion. But as we've seen before, we can do a rotation into a reciprocating motion. No? So if you can imagine this example, this animation here, you can convert rotary motion into sliding, no, or reciprocating motion. So this is called a slider and crank, no, mechanism. So you have a slider, this block here that slides through this slot here, and then you have a crank, no, the crank that drives this mechanism. No? So usually we utilize this for combustion engines or internal combustion engines. It's quite important, no, for compressing and decompressing the air fuel mixture. No? So if you can imagine, if let's say you have a four-bar linkage, and you imagine that CD and AD are infinity, no, you can make this infinity. You can imagine, just imagine that it is infinity in length, no. Then if you create this or you make this C as a slider, no, then it will be linear in motion, no? Comparing this to a finite value of AD and CD. No? So if you can imagine, if this is just a 4-bar linkage, it can slide off this rotary motion. It can rock, no? It can rock in this motion. But if it is long enough, so that the radius is big enough, as you can see, if the Earth is very big, no, the one we are standing on seems to be linear, no? If the circle is very big, as it goes bigger and bigger, the flatness, no, or the curvature seems to be going to zero. So basically, a slider and crank mechanism is still a 4-bar, no, technically a 4-bar linkage, but the other links, the two links, no, there's two links, the frame and this rocker is has a length of infinity. Okay, it is that simple, no? So it's still a 4-bar linkage, so it will be simple for us. No? So another definition that we should take note of is the offset. So the offset is the E here, which is just this difference between or the this height, no, from point A to point C, which is technically defined as the difference between L1 and L4, which are our frame and our rocker, no, as we've defined earlier. So L1 here is the frame, L4 here is the rocker or this CD. So the difference between these two is called this offset E, which is also the height, no, incorporated from A to C, the perpendicular height, no. So um, just to define, no, if a slider and crank mechanism is a Grashof chain, meaning we have to identify if A and B, no, if A and B can fully rotate, no. If it is not a Grashof chain, then A and B cannot fully rotate. So we have to identify if this is a Grashof chain or not. So basically, using the Grashof's criterion, we can define the largest length as the, let's say, it could be L1 or L4, no? Basically. But the smallest link here, or the shortest link, is L2. So, but we can also define the distance, no, or the offset distance as E, which is the difference between the two. So we have an absolute value because the max can be L1 or L4, no? We do not know because they are both infinity. So if we recompute this again, we can see that to be able to identify if this is a Grashof chain, we just add the shortest link plus the offset distance. And if this is less than the link, the other link, which is in this case L3, then it will be a Grashof chain. So A and B can fully revolve. Okay. Now for the inversions, no, of the slider crank mechanism, if we set the slider crank mechanism to an offset distance of E is equal to 0, then as you can see, this will be just literally inline, no? So you don't have an offset, it will be inline. So if you rotate this crank L2, which is this AB link, then you can see a sliding motion from left to right, no? It has no offset. So if you want to, let's say, identify, for this example, I think we want to identify if this is a Grashof's chain. Then we can compute this shortest link, no? So the shortest link is L2. The largest link, of course, is L4 and L1, which is infinity. But we can identify the offset, which is basically just the perpendicular height from A. Then this would be 0. And then this is still the larger than 62.5, which is L3, the other link. Then it is called a Grashof chain. And then AB can fully revolve, no? So an inversion of this mechanism, or the slider crank mechanism, is the quick return mechanism. So the first thing about this quick return mechanism is we have to take note of the what, no? We have to take note of a new, no, sliding pair. So we have another sliding pair here, or a new sliding pair. Sorry, not really a sliding pair, but we have to take note of this connection between L1 and L3 and 4, no? So as you can see here, this AD uh, is like what do you call this? A slider. Well, not a slotted, no, a slot for the slider C, wherein it can where the slider C can fully slide between this AD most of the time, and L3 can fully revolve, no, or this BC link can fully revolve. So for this example, no, of this quick return mechanism, we have the crank and slotted lever. No? So basically, we just added another extra link at the end of AD, which is this E. So, sorry, not this one. So, as you can see, if we fully rotate this crank BC, the slider E will reciprocate in between, no? Left to right. Okay, so the slider C here can slide between this AD, no? And the slot, no? We call this the slot, this AD, because it is slotted, no? Right? So, this is an example of the crank and slotted lever, no? So, comparing this to this, no? So, you can rotate this BC, okay, this length, and then A and B are fixed, no? As you can see here. And then you can create this quick return mechanism. So, it will quickly return after that long revolution. Also, that's it for crank and slotted lever. So for Whitworth quick return mechanism, at this time, so we will now attach the connecting link at the bottom, no? No? At the bottom of the slider, no? Or the slotted lever AD before. So you have AD, you extend the AD to the other side, no? Comparing this to the top, no? So the other side. Then you will have a Whitworth quick release mechanism. So how do you imagine that now? So as you can see, it is quite different from the crank slotted mechanism. No? It feels like it has a longer, no, revolution. Okay. So moving on from quick return mechanism. So quick return mechanism is the first inversion of the slider crank mechanism. We also have a different mechanism for slider crank, no? Which is the oscillating cylinder mechanism. So in this case, what we can do is we can fix, no? We can actually fix the L3 here, no? In this case, the intermediate link, no? So if you fix this link L3 based on this slider crank mechanism, then what we can do is we can slide the L1, no? And the L4, the link 4. And what happens here is this motion can happen. No? So you can rotate AB, okay? L3 is fixed, L1 can reciprocate, no? As you can see, this is an example of the steam engine. Okay, so another inversion of the slider crank mechanism is the hand pump mechanism. So from the word itself, it is usually used for hand pumps, no? So as you can see here, if this sliders is fixed, no? And then throughout the movement of crank AB, so if you imagine this, no? You create a lever for this ternary link AB, then you can have this motion, no? Wherein you can move the piston at around point D. Okay. So another special type of a four-bar linkage or four-bar mechanism is a double slider mechanism. No? So a double slider mechanism is composed of usually two sliders, no, from the word itself. And then you have a connecting rod or connecting link, and then you have a guideway or a guide frame. No? So if you can imagine, if you try to move B, no, upwards and downwards, no, here, then what happens to A, as long as you have a guide, it will be guided to move left and right. No? So if you go down for B, A will go left. If you go up for B, A will go right. But they have a peak, no? Peak points, no? Depending on the length of the connecting rod. So again, you have four links here. You have the perpendicular guideways, usually the frame or the guideway, L1. And then you have the slider L2, so the slider L2 can move freely. And then you have the connecting rod and then another slider. So the simplest inversion of the slider mechanism, double slider mechanism, is the elliptical trammel. So you can use this to draw an ellipse. No? So as you can see, what happens here is if L1, no? If L1, the guideway is the frame or is not moving, so L2 and L4 can freely move from each other, then you can create an elliptical trammel. So L1 here is fixed, no? So another inversion will be the Scotch yoke mechanism. So the one that is fixed here, for this example, will be L2 or L4, no? So either L2 and L4 could be fixed. And L1, the guideway will now freely move, no? So as you can see, the guideway is actually this blue rectangle here, no? Rectangular shape here, that is moving, no? The guide frame is actually moving, but the slider is not, I mean, L2 is or L4 is fixed here, okay? So another inversion of the double slider is when you fix L3. So if L3 is fixed here, L2 and L4 can freely move, including the guideway L1. No? So as you can see here, if you have, let's say, two shafts, no, and you want it to move at the same speed, but they are not properly, they are not properly aligned. You have an offset. You can use an old ham coupling. No? So in an old ham coupling, you have an intermediate piece here, which is this red piece here in the middle. And it has a guideway here, no? As you can see. It has guideway here and there's another guideway here. So what happens here is this intermediate piece can freely move, no? As you can see, it is moving, no? Something like this, no? As you can imagine, wherein it can transmit the power, no, at the same speed but with an offset. So L3 here is fixed, no? So take note of that. L3 is fixed, L4, L2, and L1 is freely moving. Okay, so that's it for this lecture. So see you guys in class.